Good morning, students. Hope you're all doing good by God's grace. Last class, we were revising Lesson 1, Introduction to Computers. Today, we will revise Lesson 2, Number System. Under Number System, we are going to see number conversions, then binary arithmetic, then types of encoding. Okay. In number conversions, you know the base value? What is the base value for binary, for decimal, for octal, for hexadecimal? I know you people know the answer, but let us refresh ourselves. Okay, for the binary, the base is 2. The by, in binary, by stands 2. So the base value is 2. The digits are 0 and 1. For octal, the base value is 8. The digit starts from 0 to 7. So total 8 bits. Okay. For decimal, the base value is 10 and the digit starts from 0 to 9. For hexadecimal, the base value is 16. The digit starts from 0 to 9. Then for 10, it is A. For 11, B. 12, C. 13D, 14E, and for 15 it is F. Okay. Now let us look into some examples. First one, steps to convert binary to decimal number. Step 1. First, you have to write the positional value for each bit. For a given binary number, you have to write the positional value. Second one, you have to write the equivalent weight. So you have written the positional value and you have to write the weight for that positional value. Third one is that you have to multiply the weight with the binary bit, with each binary bit. Then you have to add all the values. Okay, these 4 steps will be followed for converting octal to decimal, hexadecimal to decimal. The only difference is for binary, your positional value will be 2 to the power. For octal, it will be 8 to the power, and for hexadecimal, it will be 16 to the power. Okay. Now my binary value 1011 base 2, I am going to convert it into decimal. So I am taking each bit in the binary value. First one is 1, second one is 0, third one is 1 and fourth one is 1. Then first, as in the steps, first step I have written the positional value. For this 1, it is 2 to the power 3. For the 0, it is 2 to the power 2. For this 1, it is 2 to the power 1. And for this 1, it is 2 to the power 0. So that is my first step. Second step, I have to write the weight, equivalent weight. So to the power, I have written to the 2 to the power of some values, right? So I have written the values. So 1 into 8 plus 0 into 4 plus 1 into 2 plus 1 into 1. 2 to the power of 0 is nothing but 1. Can you see here? Now I have added 1 into 8 is 8, 0 into 4 is 0, 1 into 2 is 2 and 1 into 1 is 1. Then Fourth step, I've added everything. 8 plus 0 plus 2 plus 1 gives me 11. So this is the decimal value. So this is how you will convert from octal to decimal, from hexadecimal to decimal. Okay, the difference is we'll change the value of the positional notation. Jasmine, can you tell me the steps to convert octal number to decimal number?
Yes, miss. First step is to write down the octal digits and list the powers of 8 from right to left. Second step is to write its equivalent weight. Third step is to multiply each digit with its corresponding weight, and finally we have to add all the values.
Okay, my second conversion is binary to octal. So first I will group the given binary number into 3 bits starting from right to left. Example, the binary number 10110 I have divided into 3 bits. Okay, the first 3 bit is 110. Can you see this? Okay. My second step, if my grouping of 3 bits is less than 3 bits, then what will I do? Then I will add 0 to the preceding number. Can you see this example, children? So 10110 is my binary number. First I grouped it into 3 bits. But for the second set, I don't have 3 bits. I have only 1 and 0. In this case, I will add a 0 to the preceding number. Okay, add 0 to the preceding number. Then what is my third step? Then I will write the octal equivalent to each group. Okay, so for the first 3 bit, first grouping 110, the octal value is 6. For the second group 010, my octal number is 2. So this is how we will find binary to octal. Okay, so for my binary number 10110, my octal number is 26. Okay, I've converted binary to octal. How will I convert binary to hexadecimal? Same procedure, but only difference is instead of grouping 3 bits, we will group 4 bits because it is an hexadecimal. We will convert the binary number, we will group the binary number into 4 bits starting from right to left. Other steps remains the same. Then how will I convert hexadecimal to binary? If a given hexadecimal, for example 26F is my hexadecimal, so I have to convert it into binary. So for each hexadecimal value, for F I will write its equivalent binary value. For 6 I will write its equivalent binary value. For 2 I will write its equivalent binary value. Then I will join the 3 sets of binary number. This gives me the binary value, okay, for the given hexadecimal. Children, what is the base value for binary? What is the base value for hexadecimal? You're right. The base value for binary is 2. The base value for hexadecimal is 60. Next, we are moving into ones complement. What is ones complement? Let's look into it. Step 1. First, we have to convert the given decimal number into binary. Let's look into an example. For decimal number 24, I have to convert it into its equivalent binary value. So I will do LCM and find the corresponding binary value. So for the number 24, my binary value is 11000. So that is my first step. My second step, then I have to check whether the converted binary number contains 8 bits. If the number is not 8 bit, then what should I do? I should add 0 to before number. Okay, since my binary conversion is not a 8 bit, I've added 3 zeros before. That is before to the most significant bit, so that it becomes 8 bits. Then third step, then I will invert all the bits. That is, my zeros will become ones and my ones will become zeros. So can you see here? So all the zeros are turned into 1 and ones are converted into zeros. Okay children, so this is how we will convert 1's complement. Then 2's complement. Step 1. First I will do 1's complement, that is decimal number. I will convert it into binary. I will check for 8 bits of number, for 8 bits. If that binary digits don't have 8 bits, then I will add 0 before MSB, that is most significant bit. Then I will convert all the ones into zeros and zeros into 1. This is my 1's complement. Then I will add the fourth step for 2's complement is add 1 to the result to the LSB. So you will add 1 to 1's complement. Let's look into an example. 24 is a decimal number. I am converting it into binary and I am checking whether the resultant binary number has 8 bits. It is not 8 bit, so I am adding 30 before the most significant bit. Then I am converting ones into zeros and zeros into 1. That is my 1's complement. Then I am adding 1 to the least significant bit. When I add, the result is 111010000. So this is my 2's complement. Okay. Joshua, can you tell me the steps to convert the given decimal number into 2's complement?
Yes, miss. The step 1 is to convert the given decimal number into binary. Step 2 is to check if the binary number contains 8 bits. If it is less, we need to add 0 at the leftmost bit to make it as 8 bits. Then step 3 is to invert all bits, that is, change 1 as 0 and 0 as 1. And the final step, fourth step, is add 1 to the result to the least significant bit.
Then moving on to binary arithmetic. So first is binary addition. So for binary addition and for binary subtraction, we have some rules to be followed. Let's look into the rule for binary addition. If I'm going to add 0 plus 0, then my sum will be 0, my carry will be 0. If I'm going to add 0 plus 1, sum is 1, carry is 0. 1 plus 0, sum is 1, carry is 0. And finally 1 plus 1, sum is 0 and carry 1. Let's look into an example for binary addition. Before doing addition, you should just write the rule in your rough column so that it is easy for you to look into the rule and work out the sum. So my binary number is 1100 and 0100. I'm going to do addition. Okay. So for 0 and 0 in the table, my sum is 0. So I'm writing 0. And again for 0 and 0, my sum is 0. For 1 and 1 in the table, it is 0 and 1. So I'm writing 0 here and I'm just carrying that 1. Then again I'm going to add 1 and 0. When I look into the table, for 1 and 0 is 1. So with this 1, I'm going to add the carry as well. So 1 and 1 is 0 and 1. So this is how we will do the binary addition. Now moving on to binary subtraction. So here we have some rules to be followed, same as binary addition. The first rule is, for if I'm going to subtract 0 minus 0, then my difference, the result will be 0, the borrow 0. Second one, if I'm going to subtract 0 minus 1, then my result will be 1, that is the difference is 1, and borrow 1. In this case, here we will do like the normal decimal subtraction. If my top value is 0, then what should I do? I have to borrow from the before number. Okay, so I will borrow and then work out that particular set. Subtract the particular set. The third one is, if I'm going to do 1 minus 0, then the difference will be 1 and the borrow will be 0. The last is, if I'm going to subtract 1 minus 1, the difference will be 0 and borrow 0. This rule is a default rule where you have to remember while doing your subtraction sum. Finally, we are moving on to the encoding system. Like in a previous class, Shiba Miss would have taught you that whatever we give input in the system, the machine reads the system, the keyboard value into its own language, that is machine readable language. Okay, so this machine readable language, that is the encoding system, there are different types of encoding systems. We are going to look each one in detail. First one is the BCD, binary coded decimal. Okay, this is the first encoding system. It handles 64 characters. The second one is the ASCII, that is American Standard Code for Information Interchange. Okay, the full form for ASCII is American Standard Code for Information Interchange. It can handle 128 characters. Okay, that is 2 to the power of 7 bits. The third encoding system is Extended Binary Coded Decimal Interchange Code. Okay, this is similar to the ASCII code. It also handles 256 characters, that is 2 to the power of 8 bits. Then comes the Indian Standard Code for Information Interchange. Okay, this also handles 256 characters. And the last encoding system is Unicode. Okay, this is used in a modern computers. It can handle 65,536 characters. Okay. The encode scheme is denoted by hexadecimal numbers. So with this, we are finishing with lesson 2 revision. Children, with this video, we are sending you a supplementary video and a test. Please do not forget to look into your supplementary video and attend your test. Submit your test in the Google Classroom. We will meet in next class. Until then, it's bye. Have a beautiful weekend.